Welcome to an overview of the chapter titled Other Planetary Systems. In this video, we'll introduce a few of the key learning objectives of the chapter. In particular, we'll describe the challenge of detecting extrasolar planets and how it is being met, summarize what we can learn and have learned about these planets, and understand how other planetary systems fit in with the nebular theory. This image may not look like much, but the four labeled blips of light come from four planets orbiting a star that lies far beyond our own solar system. This image is therefore part of an incredible scientific revolution underway in your lifetime. As recently as the early 1990s, we did not know for sure whether planets even existed around stars besides the Sun. Today, we know of thousands, and the number is rapidly growing. This fact not only makes it seem more likely that we might someday find life elsewhere, but also vastly enhances our ability to understand the workings of planets, including our own Earth. The fact that we can detect planets around other stars, or extrasolar planets, is quite amazing when you consider the scales involved. Recall the 1 to 10 billion voyage scale introduced in Chapter 1, on which the Sun is the size of a large grapefruit. On this scale, even the largest planet, Jupiter, is only about the size of a marble, and Earth is smaller than the ballpoint in a pen. Yet while you can walk from the Sun to Pluto in just a few minutes on this scale, you'd need to continue a distance across the United States to reach even the nearest other stars. In other words, detecting extrasolar planets is rather like trying to see ballpoints or marbles more than 4,000 kilometers away, a problem further compounded by the fact that the tiny planets shine only with light reflected by a star that is typically a billion times brighter than they are. Given that scale, you probably won't be surprised to learn that we have relatively few actual images of planets like this one, and instead rely primarily on indirect techniques to detect and study extrasolar planets. There are two major ways in which we can indirectly detect planets around other stars. The first is by observing small motions of a star caused by the gravity of orbiting planets. The Doppler method accomplishes this by looking for alternating Doppler shifts in the light we see from a star. The gravity of an unseen planet causes the star to trace a small orbit around a center of mass, so that we see a small blue shift as the star is coming toward us, and a small red shift as it is going away. The astrometric method detects a star's motion around the center of mass by looking for small changes in the star's position in the sky. This diagram shows the path that someone could in principle be measuring for our Sun if they are observing carefully from another star. The second general method for indirect detection is through observing changes in a star's brightness as planets pass in front of it as seen from Earth. This is done through what we call the transit method, which works only when a planet happens to orbit edge-on as seen from Earth. During the time that the planet passes in front of the star's light will dim slightly. If this dimming recurs repeatedly with a regular period, we can conclude it is caused by a planet orbiting the star with that period. Each method has advantages and limitations that you should study in your textbook. Here, we'll focus next on what we can learn about the unseen planets detected by these methods. All three methods, the Doppler method, the astrometric method, and the transit method, tell us a planet's orbital period, from which we can also calculate its orbital distance. The Doppler and astrometric methods can also tell us about a planet's mass, because for a particular orbital distance, a more massive planet will exert a stronger gravitational tug on its star. The transit method can tell us a planet's size, because a larger planet will block more of its star's light during a transit. Before we continue, use what you've learned here and in prior chapters to answer this question. Which method or methods can tell us a planet's average density? Can we learn density from each of the three methods individually? From the Doppler method by itself? From the Doppler and astrometric methods together? Or from the Doppler and transit methods together? The answer is D, the Doppler and transit methods together. In that case, we will know the planet's mass from the Doppler method, and its size and hence its volume from the transit method. And knowing both mass and volume allows us to calculate average density. This table from your textbook summarizes the methods that can be used to measure each property. Today, we have data for enough planets that we can begin to draw statistically based conclusions about planets in general. Perhaps most remarkably, we can now say with confidence not only that planets are common, but also that planets similar in size to Earth are common. This graph shows current estimates of the percentages of stars that have at least one planet of various sizes. For example, this bar shows that about 17% of stars have at least one planet similar in size to Earth. In fact, these percentages are almost certainly underestimates that will rise as more and better data become available. Data on planetary properties have also enabled us to learn that planets come in more than just the basic terrestrial and Jovian types that we find in our solar system, an idea discussed in the narrated figure titled Planetary Properties by Mass and Radius. Finally, studies of other planetary systems have helped scientists both to confirm and refine the nebular theory. One key confirmation comes from the fact that the theory predicts that planets should be common, and we now know that they are. At the same time, we've discovered a few surprises that tell us the process of planet formation can be more complex than what the simplest version of the nebular theory envisions. For example, the fact we found Jovian-sized planets orbiting close to their stars tells us that planets sometimes migrate inward from the orbits with which they are born, perhaps as a result of waves propagating through the disks of gas in which planets form. To recap, in this video, we have described the challenge of detecting extrasolar planets and how it is being met, summarized what we can learn and have learned about these planets, and understood how other planetary systems fit with the nebular theory. I hope this will help prepare you for your follow-up reading in class time and suggest that you follow the study plan outlined in the How to Succeed section of your textbook's preface.